Welcome to another Advent of Code walkthrough video. Today we'll be looking at 2022 day 24. Okay, so we're leaving to our extraction point now, and partway up the mountain is a flat open area. It's a bit of the climb, but it's not too bad. Normally that would be true, but unfortunately the mountain is covered in snow, which is more difficult than what we're used to. And so we reach a valley that must be traversed, but we find a bunch of strong turbulent winds that are pushing around small blizzards of snow and sharp ice. We'll need to avoid the blizzards. Fortunately, we can easily see all of this from the entrance to the valley, so we make a map. So here's our map. We start in the top left here, in this gap, and the bottom right is our destination. These pound signs are the walls in the valley, everything else is flat ground that we can all walk across. Clear ground is drawn as a dot, and otherwise blizzards are marked with a little arrow, indicating the direction of their motion. So here we have two blizzards. This one is going to the right and this one is traveling down. After 1 minute, each of them moves in their appropriate direction once. Because of conservation of energy, when a blizzard reaches a wall, a new blizzard on the opposite side forms in the same direction. So after 1 more minute, this blizzard moves to the right by 1 again, and this blizzard, which has reached the bottom wall, now warps around to the top. Because the blizzards are made of tiny snowflakes, they can go through each other, and the wind that pushes them around also operates independently. So in the next frame, these two blizzards will be in the same location. And after 1 more minute, they'll pass through each other and end up in different positions again. So there's no collision mechanisms, the blizzards just phase right through each other. And after 1 more minute, of course, this rightward going blizzard will wrap around again. The process repeats seemingly forever. And so the board state basically just keeps cycling. So one immediate observation we should make here is that the board state will be the exact same after a certain amount of iterations. Each row cycles r times. Let's call the width of the board r and the height c for, the width c for the number of columns and the height r for the number of rows. After c iterations, every c iterations, each row will be in the exact same configuration as before. And after r iterations, each column will be in the exact same configuration as before. And so if we take the LCM of those two, which is the smallest number that is a multiple of both, then every that many number of times iterations, the entire board state will be the exact same. And this time, unlike with the monkey tossing problem, this actually matters. So here we see the width is 6 and the height is 4. No, this is the example that we're supposed to look at. So this is a more complex example, which is what the sample input will run us through. So this has a width of 6 and a height of 4. If we just naively took the product, that would be 24, whereas if we take the LCM, that's 12. So that essentially lets us cut our total states in half, which doesn't seem all that important, but when we look at the actual input, this input is 120 wide and 25 tall. And so if we take 25 and 120 and multiply them together, we get 3000. But their LCM is only 600. So we can cut down our states 5-fold, which becomes quite impactful over the long run. But let's see what we're actually trying to do here. Okay, so we begin in the non-wall position in the top row, which is always in the first column. And we want to end up in the empty spot in the bottom row, which is always 1 column from the right. Okay, so this is an example of how we can get there. So initially we're here. We can move down by 1 in this minute because we move simultaneously with the blizzards. So we can move down even though there's a blizzard presently here because in the next frame it is moved away and no other blizzard will move into this position. And we can keep navigating around, sometimes even backtracking as necessary, and eventually we will be able to move to the clear spot once all of the away from all of the blizzards. The question, therefore, is what is the fewest number of minutes required to get to the extraction point? To exit the valley. So let's paste in our test input and our real input first. So the first step is to parse the grid. So we're going to keep track of the blizzards, and we're going to divide them into 4 groups based on their directions. And you'll see why I do this in a bit. Okay, and now we can do for r line in enumerate open 0.lines.splitlines. read the split lines, and we want to discard the first row. And the reason for that is so that the topmost row will be aligned with 0. This just makes wrapping easier because of the modulo operation. So we're going to chop off the first row, and then we'll do the same with the first column, like so. So now our iteration starts here actually, which is fine because the outermost, the top and left row and column are always the same and we don't actually need to read them. So now we can just see if item is one of the blizzard characters, then we will add it into the appropriate blizzard. So the order in which we add them doesn't really matter, we just need to stay consistent. So blizzards, let's index the item in our string of characters, dot add the row and the column. And this time I'm not using complex numbers because we'll need to do modular arithmetic, and that's not supported with complex numbers. Okay, so now if we print out our blizzards, we should have collected all of the blizzards on our board. So that's a list of blizzards. These are all facing left, these are all facing right, these are all facing up, and these are all facing down. Okay, so this is a pathfinding problem because we have an initial state and a target state, and we can make individual steps through each state transition. So we're going to do this via breadth first search because it's not a tree, so we can't really do depth first search, and it's also not actually brute force. We'll also preemptively import math because we'll need it for LCM. Okay, so let's implement the core of our pathfinding first. So consider what we need in our queue. Now you might be inclined to say that we need to track the distance moved so far, or how many minutes have passed, sorry. The current position, which is going to be, we start just above the top row, so the row is -1 and the column is 0. Actually, we can keep that all flat. And you might be tempted to also include the list of blizzards and mutate it each time. So this approach would lead to us modifying the list of blizzards each time to shift them. However, that is actually not efficient. Shuffling around all of the blizzards every time is actually quite a slow operation. What we can do instead is we realize that we don't actually care exactly where the blizzards are. We just need to see if the space that we're trying to occupy would collide with a blizzard. So what we can do is, instead of shifting all of the blizzard positions over and then checking if we will collide, we can shift ourselves in the opposite direction, which only requires one shift, and then check for membership, which is a much faster operation. And this also simplifies our state because we no longer need to keep the blizzards as part of the state. So now we just do the standard queue implementation, queue-based BFS implementation. While queue, distance, or I guess time, because we could be waiting in the same spot, time, current row and current column equals queue.popleft. Okay, so now we consider each of the possible next states. So for dr, there'll be deviation in row and deviation in column in all of the possible moves. So that'll be move to the right, move to the left, move up, move down, and stay in the same space. For each of these, we will first test if it is our target. So where is our target? So one thing to note here is that because of Python's scoping, R and C still exist even after these for loops have ended, so R will be equal to the index of the last row. And since the last row is equal to all these pound signs, it is actually equal to the number of rows that are relevant to us. So we will end up in the row just above the last one, so that would be in row R plus 1, or no, in row R. And we will end up in the second rightmost column, so that's C minus 1. So now nr, which is next row, equals current row plus change in row, and nc equals cc plus dc. If we have reached the end state, we actually do not need to check for blizzards. In fact, a blizzard check would actually fail here because of the way we're going to implement it with our logic. So if nr nc is equal to the target, we can just print out how long we've waited and exit the program entirely. And I'm actually going to add a thing up here. You'll see why later. I'm just going to increase the time by 1 as we enter the state. Otherwise, we need to consider if we'll cause any collisions here. To do that, we'll do we'll need 3 variables. The direction, so the index within the blizzard sets, the shift row and the shift column. So for test row and test column shift so the first one was moving to the left, so we'll do 0, -1. The second one was moving to the right. The third one was moving up. And the fourth one was moving down. And this time we don't have a stay in the same space thing because none of the blizzards are staying still. Then we will check. So how do we check this? Well, instead of checking all of the blizzard positions and shifting them by TRTC, we take NRNC and shift it backwards in the opposite direction of TRTC. So that would be NR minus TR times the amount of time. And this time variable here needs to be the time of the next state, which is why I added 1 to it here to avoid needing to do the +1 here. And we do the same NC minus TC times time. Now we just need to take these and wrap them over the number of rows and the number of columns. And if this state is in the blizzard set of that direction of blizzards, then we break. Otherwise, if we didn't break out of the for loop, that means that we don't have any collisions with blizzards, so we can add this state to our queue. Queue.append, and the next state will be the time +1, which we've already incremented, and NRNC. So we see that by doing this instead of transitioning the blizzards themselves, not only does this save a lot of time, it also means that we save a lot of space that we would have had to use to write the code to shift all the blizzards. And we also carry a much simpler state. And reducing the size of your state will actually end up mattering quite a lot because A, you could run out of memory, B, your program tends to get really slow once you start consuming a lot of memory. And so theoretically speaking, this would work. Now let's implement the second optimization, which is that every LCM times the board is the same. So if we're in the same position, and we've already seen this a multiple of the LCM times before, then we're wasting time exploring the state again, because we are functionally in the same state because all of the blizzards will have wrapped around to their original positions. So the LCM of 2 numbers is equal to their product divided by their GCD. Be careful that this is not generally true for more than 2 numbers. You can't take their product and divide by the GCD, that will not work. However, for 2 numbers, this is correct. So we'll now add a scene set, which will track where we've been. And we don't want to track the initial state because it doesn't actually matter. We also, one other thing that I almost forgot about. We also need to make sure we don't run into the walls of the valley. A, this could cause us to short circuit around the blizzard. B, this also causes our state count to grow infinitely because we just go off in infinitely many directions. So if we want to implement this check after here because this would be treated as a wall in our logic. If NR is less than or equal to less than 0, or NC is less than 0, or NR is greater than or equal to the number of rows, or NC is greater than or equal to the number of columns. And we also need to make sure that we aren't banning the initial state because we might need to stand there for a while. And NR is and not NR and C is equal to the original state, which is -1, 0. Then we will skip this state if we would run off the grid. And the optimization we will add here is the key, which will be used to as a sort of like unique identifier for our state, is going to be the current position and then the time modulo the LCM. If we've seen this state already, then we skip it. And otherwise, we will add the key to our scene set to mark it as visited so we do not visit it again. Okay, and so not too surprisingly, this doesn't work first try. Let's try to take a look at what's wrong. Okay, so this is going to be very messy, so we won't really be able to read the output, but it can potentially expose obvious errors. Okay, so that is an obvious mistake because it means that we're not actually pushing anything into the queue. So if we're not pushing anything into the queue, that indicates that one of these checks is causing issues. So we'll print skip here to indicate that a state was skipped. We skipped 4 states. Okay, so given that we were only checking for 5 states, that is a fairly obvious error. And if we print out NR and NC, we notice that all of our next positions are actually invalid, it seems. And yeah, this is where it's revealed that I don't know how to type. These are meant to be up and down. I was typing 2 rights and 2 lefts. Okay, and so this seems to work perfectly fine. And if we run this for a bit, it's a bit slow, but yeah. This gives us our puzzle answer of 264. So just to revisit this a bit, because the next part is quite straightforward, the first optimization we make is that we can only consider states that differ by something that isn't a multiple of the LCM. If the time is the same modulo of the LCM, that means that the board state is the same because it cycles every LCM minutes. And so we can use this to cut down on our state count drastically by skipping over things that are functionally the same. Additionally, by not shifting the blizzards, we can instead shift ourselves in the opposite direction of the blizzards to check if we would collide with a blizzard in that position. Moving on to part 2, the elves have one of the elves forgot his snacks at the entrance. So because we're so good at dodging the blizzards, they humbly request that we go back for the snacks. So from the same initial conditions, what is the minimum amount of time needed to go from the start to the end, back to the start, and then back to the end? To do this, we just need to implement a couple more additional steps in our logic. So we now have a list of targets. The first target is the end gate, and the second target is the start gate. We're also going to add a new item into our state, which is going to be the stage. The stage is going to is what I call basically which leg of our journey we're in. So stage 0 is the initial path, which was part 1. Stage 1 is the backtrack, and stage 2 is returning to the exit. And so we can find which target we're at by just doing the stage modulo 2. So we'll change this check to targets of stage modulo 2 and add stage into the thing we pop off from the queue each time. So instead of exiting every time we reach our target, we only do that if we've reached the target and our stage is 2. In other words, we're in the last leg of our journey and we get to the end gate. Otherwise, we don't actually exit, but instead I'll keep track of something that I'll call end stage, which will be the next stage of our given move. If we reach a target but we're not in the final stage, we increase or advance our current stage, marking that we want to go to the next segment of our journey. We also need to add an extra check here. We're not only checking for the start gate because we might also need to wait around in the end gate. So we're going to say and NR and C not in targets. Targets is basically the list of our 2 gates. So we want to skip if we're in a gate. Additionally, we don't want to do blizzard checks if we're in the gates because the gates do not have blizzards in them. So we can skip over this by doing a bit of wraparound logic. We'll do it this way. Fail equals false. And then if NR and C is not in targets, then we will need to check this and we'll mark fail equal to true here. And instead of relying on the built-in for else thing, we'll just do if not fail. Okay, and finally we need to remember to push on end stage each time we're done. So that also does not work. Oh yeah. The final thing we need to remember to add is the stage into our key, because if we end up in the same position at the same equivalent time, but we're in a different segment of our journey, we can't skip the state because the part before us isn't necessarily the same. And this gives us our puzzle test output of 54. And for the puzzle output, this program will take a longer time to run. I'll run it in PyPy just to save on time. And also pause the recording here just so you don't have to wait around. Okay, and this gives us our final output of 789. So overall, a fairly straightforward problem. I didn't place on the leaderboard because honestly, I can confidently say that I'm just very weak with pathfinding problems in general. I've consistently performed poorly on them, and this year there's just been quite a lot of them. So that's something that I expect myself to improve on a lot in the upcoming year, because clearly I need more practice with it. But overall, a fairly straightforward problem. Compared to the past few days, definitely very refreshing to see something comparatively straightforward that didn't require a lot of annoying caveats to it. So thank you for watching. That's all for this video. I hope you enjoyed and learned something, and I'll see you tomorrow for the final day of AOC 2022. Thank you.